Alright, so if I was usually solving a trig equation, I would try and use an identity to make sure everything's in sines or everything's in coses or everything's in tans. But here we've just got single angles and it doesn't seem like we can use an identity. So you can see it's a cos minus a sine. So what I can use is the compound angle, remembering that if I want a cos minus a sine, the compound angle, I'm going to use something like the expansion of, let's go r cos theta plus alpha, because remember that gives us a cos and then a minus, cos minus sine sine. So if I expand that out, I get an r, let's go like this, cos theta, so cos minus sine sine, sine A, sine B. Now, when I do that, I can now compare to this what I do have there. So can you see that if I just write this a little better, I'll put the r cos alpha out the front, and then I'm going to put cos theta minus, you've got the sine theta already there, and then I'm going to put the r sine alpha here. So I'm just putting everything in a different order, but then you can see if I write under it 2 cos theta minus sine theta, and in this case there's nothing after the sine theta, so that must be times 1. We can compare those things. You can see from that the r cos theta, let's do r sine theta first, the r sine theta alpha, would equal 1, and the r cos alpha would equal 2. Now, if I just did the first expression divided by the second expression, r divided by r is 1 sine on cos of the same angle, it becomes tan. So I'm getting tan alpha equals a half. So I know that alpha is the inverse tan of a half. The other thing we can do is square both those terms and add them together. So r squared sine squared alpha and r squared cos squared alpha. So I'm really doing 1 squared plus 2 squared. And we know that's 5. And over here, remember, if I factorize, I'm getting sine squared alpha plus cos squared alpha, which we know is, 1. So we've really just got r squared equals 5, so that gives us r is, if we just want the positive one here, is root 5. So I can put that back in up here for this expression here. And I'm replacing it for this original one, because we couldn't put everything in terms of sine or cos, but yes, now we can use a compound angle. So we're saying that root 5 cos of theta plus our alpha, and our alpha, I'm just going to write alpha, but it's inverse tan of a half, is equal to 1, and we're solving that. So cos of theta plus alpha, we know alpha is 1 on root 5. Just like normal, remember, cos of some angle is a positive 1 on root 5. So we're looking in this quadrant and this quadrant if we're going between 0 and 360. So the theta and the 360 take away theta is what I want. So I'm going to have theta plus alpha equaling whatever inverse cos of 1 on root 5 is. But I'm also going to get 360 minus whatever inverse cos of 1 on root 5 is. And then to find theta, I'm going to subtract alpha from each of those. So in the calculator, I'm doing inverse cos of 1 on root 5, and I'm subtracting what's alpha. Alpha comes from over here, is inverse tan of a half. But I'm also doing 360 minus inverse cos, be careful in your calculator, of 1 on root 5, and minus inverse sine of a half. Alright, so if I do those two things, check my answers please, but what I got was 36 degrees. Remember, we're in degrees because it said 0 to 360 here. 36 degrees, 52 minutes, and an exact 270 degrees for that one. So this up here is a bit of an explanation. I'd like you to practice it so you're deriving it each time and just checking. But really, in the end, you can just remember that r comes from, so when we want our r out the front, we're just using Pythag on the coefficients of the sines and the causes, so 2 and the 1. So it's a 2, 1, root 5 triad, so we've got root 5 there. And then to find the angle, we're using our in this case, the 1 on 2, so inverse tan of 1 on 2. But it's nice to know where everything comes from and just practice doing that till you've really got it.